All right, so I got momentum progress check. Free response question, the second one. So it's lines 30 and 31 has two problems in it for the progress check. I thought they were both decent questions. This one's a shorter one. And the reason this one made the cut for me as to one of the ones I wanted to get done earlier is there's a concept here. And part of me wants to just explain the concept in advance, I think. And then we'll see how it applies here. At least we'll look at it. So here's the deal. Momentum is a vector. You know this. You bright people, you know this. So what I don't know is where my ruler is. Hold on. There's the ruler. All right. So we can look at this a couple different ways. We'll look at it like they show it in their picture, but I also want to look at it from, say, the other direction with a vertical situation. All right. Although it's more likely to be the case with the horizontal. So here's the deal. The ball that comes in at an angle. So we'll say it's coming in like this. It's going to hit right here. This is the direction it's going to come in. So it has this velocity. That velocity is both in the x and the y. And so the momentum gets split into you look at the momentum in the x and the y. So I don't know if I know the angle, but you know what? I don't care if I know the angle right now. We're just going to say, based on the drawing here, this is my x component of the velocity. And this, in green, is my y component. And then there is a course, if you wanted to, I could call this one, if I multiply it by the mass, I could call this vector the x component of the momentum, and this the y component of the momentum. Let's face it, the mass ain't changing. Okay? So, here's the thing. And it bounces off of this. And say, we'll pick it up again over here. Assuming it's going the same speed, we don't lose anything. But if it's going the same speed, it still has an x component and a y component. One of them doesn't change. One of them is left completely alone. It's your x in this case. Why? Because the force, the external force that's going to change the momentum of that ball, is the normal force by this surface. And that can only point y, right? It can only point up. So the y momentum does change. It goes, in fact, it's changed. If this velocity was -10, this would be +10. And the change in y velocity would be 20. Right? It would be double. Remember the whole bouncing off thing. But the change in the x would be nada, nothing. So it's kind of like if you think of projectile motion, where gravity only affects the y and the x is left alone. Similar thing here. You could say that in this case, if a bounce happens fast enough off of a vertical wall, you could argue that the y doesn't change, but it would a little bit because it would be speeding up because of gravity. That's why this situation is a little bit easier. I mean, if it happened over a small enough distance, the increase in y velocity would be negligible, but it would be there. So, but the x would be changed by the wall, and the y would be changed by gravity. But in this situation, gravity isn't affecting this at all anyway. And once again, they're saying it happens so fast that, yes, this y velocity will probably be a little larger here, but it will slow down by the same amount here. So at these two levels, it'll still be the same. But the key here is that the momentum, the change in the momentum in the x is 0. The change in momentum for the y is going to be double the initial momentum, whatever it is, because it's going to, if it leaves as fast as it comes out, presumably. All right, so that's the idea there. Now let's see how they, probably not the only idea in this, but we'll see. So they establish positive, negative, which is important because the magnitudes of these are the same, but it's the fact that one's going to be negative, the other's positive, that's going to create this double thing. Ball is thrown towards the ground. The figure shows the direction of the ball before it reaches the ground and the direction of the ball after it bounces off the ground. After the bounce, the ball leaves the ground with the same speed that it had before the bounce. Okay, usually doesn't happen, but we're good. The angle between the ground and the ball's theta. So the angles are the same as well, so that's cool. Okay, so we have that. So, great. Now what are you going to ask us about it? Each grid below represents a component of the change in momentum of the ball as a result of the bounce. On each grid, draw a vector arrow to indicate the direction and relative magnitude of the change in momentum of the ball as a result of the bounce. If there is no change in momentum for a given component, write no change under the corresponding grid. Okay. So first of all, based on what we just talked about, the horizontal dimension, there's going to be no change. Its horizontal speed, and therefore its horizontal momentum, will not change. That component of this velocity. So you can call this the momentum, actually. To hell with it. Let's just call that the momentum. So this dark line is the initial momentum of the ball. This red line is the initial x component of the ball. Now, technically speaking, this momentum arrow would be located, so it's this long, it would be located off like this, along that line. So this would be the final momentum of the ball. And it would have an x component, and they would be the same as the beginning. So the momentum x final would be the same as the momentum beginning. There is no change. So that's why the first thing we're going to do is say horizontal component. They say to write under the corresponding, so no change. The external force that's going to change the momentum is the normal force, which is vertical. That's going to change. Ooh, wait a second. That's a hint. Which way? So first of all, which way is that force by the normal force got to be? It's got to be up, right? Ball hits wall or hits floor. Floor hits ball. So I'll write in pencil. So this has got to be a vertical arrow. It's got to be. Because the change, it was going down and it ended up going up. So the change is up. Now the question is, what do they mean by the relative size of the arrows? Relative magnitude to the change in momentum of the ball as a result of the bounce. If there is no, so I'm now trying to figure out. I mean, if there's a change, I would say, let's scale. Like, they don't even give us numbers, right? I guess all I would say is I would make it an even number, like 2 and 2, or 1 and 1, or even 3 and 3, because that shows that you recognize that half of the change went to remove. Hold on. So half of that change went to remove this y component, the initial y component, and bring it to 0. And then the other half of the change went to raising it up the same amount in the other direction. So I would definitely not make this 3 blocks or 1 block or 5 blocks. I would make it an even number of blocks. We'll look at the answer in a second and see if that's a solid thing. I don't see any other indicator as to what the scale is. So I would go with just make sure I have an even number. Okay? All right, let's see what else they want. B, a ball of mass M is released. They seem to go in a whole nother direction at this point. I'm really curious now to look at the answers. Hold on. Scoring guide to see if that's all we needed to do. So no change. They did not write it under the graph like they said. They should lose those points. 1, 2, 3, 4. So they wrote this one 4 long. So let's see. That one was. Did they really give you 5 points for that, mother? How? Unless this is a different part. Oh, part B, 5 points. Okay, yeah. For this part, there's only 2. Okay, good. I was like, why that work? 1 point is earned for writing no change in the horizontal component. 1 point. 1 point is earned for drawing an upward arrow, vertical component of the change in momentum of the ball. Just an upward arrow. And why did they say that bit about scaling? Well, mine was more thorough. All right, this next part's 5 points. Let's go see what happens here. A ball of mass m is released from rest. Height h1 above the ground. After the ball reaches the ground and bounces, it travels to a height of h2. In a clear, coherent paragraph level of length response that may also contain equations and drawings and pictures of your dog. Explain why. Oh, sorry, no, your dog. No, just kidding. Explain using the momentum and conservation of energy. Why h1 h. Okay. All right. Let's give it a shot. Let's see how many of their points that I haven't looked at. How many of their fancy points I'm going to get. So. All right. I go in chronological order. Before the bounce, at H1, the ball has a mechanical energy of, well, how about this? Equal to the gravitational potential energy at that location. And I would then go like in bracket, mechanical energy, let's say before, equals m of ball g h1. All right. So we've established that it has that amount of energy. This will also be, should I say this will also be, this will, due to the conservation of mechanical energy, this will be equal to the KE of the ball just before it hits the ground. Okay. And then I would say, during the impact with the ground, some of this mechanical energy is converted to heat. Due to, I'm going to say due to the word you want to use here is the deformation or deformation of the ball. due to the maybe due to heat, due to the friction. How about that? Due to the friction. Hold on, I lost my video here. Due to the friction created that occurs, we'll say created during the deformation. So point out that there's friction in that deformation, not just that the ball is bent, not just that the ball's surface is bent, but that there's friction as the molecules are stretched against each other. That means the KE of the ball after the bounce you know what we could say here? We should probably say we know that this is going to be true, but we're going to put a sentence in between. Because, or how about this? Because the collision is partially inelastic. There we go. We got momentum in there. Then we could say, I'm running out of space, but then we could say KE after bounce will be less than KE before bounce. And therefore, 3 dots, therefore, due to conservation of mechanical energy, the ball will not have the same, will have less, we should even say, will have less potential energy, gravitational, at top of second bounce. So H2 will be less than H1. Something along those lines would get most of the points. Let's find out. All right. 1 point is earned for indicating that the collision with of the ball with the ground is an inelastic collision. See, I'm glad I slipped that in there. Check. 1 point is earned for indicating the momentum of the ball immediately before the bounce is not the same as the momentum of the ball after the collision. Maybe I don't get that one. 1 point is earned for stating the kinetic energy of the ball immediately before the bounce is not the same. Okay, I did that. 1 point is earned for stating that some of the mechanical energy of the ball Earth system is converted into non-mechanical energy. So I did that, which is why it has less mechanical energy. 1 point is earned for a logical relevant. Okay, so I'm pretty logical on that. So I missed I probably would have missed this point for saying that the momentum, I use the kinetic energy more than the momentum. All right, well, blah, 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 blah. That's not bad. You get 4 points on that one. Not bad. All right.